Thank you. So I just want to link my presentation a little bit with a question that this lady was making about the number of cuts per peak. And the thing is, I mean, this presentation is going to be a little bit about these. So just want to start my presentation with a quotation of Professor Popper. Professor Popper was chairman of these HPLC conference series in two occasions, first in the 80s here in Amsterdam, and then later on in the 2000 in Maastricht. And he published a seminal paper in Journal Chromatography in the in the 90s, and he was saying, I'm just quoting him, so resolving power is all about. So we chromatographers, what we want is just resolving power. So just do some stupid computations, and we say, okay, in one-dimensional chromatography we get peak capacities in the hundreds, and more or less we know that in 1 hour we can get around 100 peaks. In two-dimensional chromatography we get peak capacity in the thousands. That means that in 1 hour we get 1,000 peaks. In 1 day we can get around 4,000 peaks. In 1 week we can get around 8,000 peaks. 1 month, this is 15,000 peaks. You want more peaks? Wait 1 year. Okay, so you get 20,000 peaks in 1 year if you do two-dimensional chromatography. So maybe I can quote this a little bit and say, it's not only about resolving power, it's also about patience. So if you are able to wait 1 year, then you get all the resolving power that you want. So that's why the title of my presentation was this. So it's not. So can we have it all? Can we have things that are fast and at the same time have resolving power? So it's going to be a trade-off between peak capacity and time. And so just to explain a little bit what happens, these dilemmas happen a lot in life. So just making a Dutch dilemma, imagine that I like beers, so I have Amstel beer or Heineken. These are two Dutch beers. So what to do? Imagine that you go to the city, in the city of Amsterdam, you want to spend around 50 euros, and you just walk around around all the, so it's about the number of bottles that you can buy of Amstel beer and the number of bottles that you can buy of Heineken beer around the cities of Amsterdam. So you can imagine that you just walk around the city, you find these shops. So these shops, for example, you can buy around this amount of bottles of Heineken and this amount of bottles of beer. And you immediately see that it has a kind of shape. And the first thing is that you're stupid if you go to this shop. Because spending 50 euros, you could get more amount of Heineken without decreasing the amount of Amstel beer that you buy. So this is kind of a non-optimal shop. This one is an optimal shop. Why? Because if you want to buy more Heineken, there's no way you can get more Heineken without decreasing the amount of Amstel beer that you buy. So that's called Pareto plots. That was introduced by Vilfredo Pareto, I think, in the 50s. So this is what is called a Pareto front. Yeah, and this example means the limit of our possibilities. So if you like Amstel and if you like Heineken, this is about what you can get if you go to Amsterdam and you spend 50 euros. So going back to chromatography, what is money is in fact pressure. So imagine that you have to spend around 400 bars in pressure in each chromatographic dimension, and now it's about having speed or having separation power. So to make this example a little bit more complicated, but at the same time a little bit easier to understand, I'm just going to change, instead of using speed, I'm going to put here analysis time. And of course what we want is low analysis time, so my Pareto front has to be something like that, because I want to be in this corner. The more in this corner I am, it means that the separation power is great and my analysis time is small. So it's a little bit different from this setup in which I was saying I want speed and I want separation power. So in chromatography we have many parameters to optimize, okay? And what we did in our paper was saying, where is this Pareto front located? If we plug in all the equations that we have in chromatography, in two-dimensional chromatography, and what are the experimental conditions that are Pareto optimal? Which links to the question of these ladies saying, how many cuts per peak were you using to have a good 2D separation? So the parameters that we were using in our study were the thing that we think is going to affect mostly in the separation power that we get in the first and the second dimension. First was the particle size, so shall we use big particle size in the first dimension, a small particle size in the first dimension? Do we have to use big or small particle sizes in the second dimension? Do we have to use which diameters are optimal for the first and the second dimension? All these things, of course, affect the peak capacity to the first dimension, the peak capacity in the second dimension. Also, the band broadenings are affected by using these different diameters. And also the modulation time, I'm going to call this A in my equations. But this also affects the peak capacity in the first and the second dimension. This is a critical parameter. Okay? So I want to pay a little bit more attention about what happens to this. So you think about what two-dimensional chromatography is. It's a system in which the detector for the first dimension chromatography is the second dimension run. Okay, so you can look at the second dimension separation as the whole detector for the first dimension separation. And it happens that, and that's known from any type of chromatography, that when you undersample your separation, it is a kind of band broadening effect due to the detector. We already know that in normal detectors. So what we did was saying, so I'm going to plug in the equation for the band broadening effects due to the low sampling in the first dimension in the system. So this is well known for everybody, so I'm not going to go into details. So what happens in the two-dimensional chromatography is that we take several fractions, and in fact the frequency of the detection in the first dimension is exactly the modulation time. Okay, so if you just plug in the equation, that's what's called a boxcar filter. So the band broadening in the first dimension, the total band broadening, is the band broadening due to the chromatographic mechanism. So we get some chromatographic band broadening, plus this term in which A is the modulation time. This is what I said. This is a boxcar filter. So peaks get apparently broader due to the fact that we are undersampling the first dimension. But this was published by Tanaka and co-workers a few years ago, and we were plugging in these in our equations. But another thing happens, and is also the effect of the band broadening in the second dimension. I think we were the first describing this effect, or not describing this effect, but plugging the equations in the optimization system. Because when you had the first solution profile and you take samples of that and you inject in the second dimension separation, there is also a band broadening effect due to the injection. We know in chromatography that there is an injection band broadening effect. And luckily enough, the equation is exactly the same with some modifications. That's also a boxcar filter, but it's modified by the flow in the first dimension and the flow in the second dimension. So again, the total band broadening in the second dimension is not only the band broadening due to the chromatography in the second dimension, but also because of this band broadening effect. That looks, so I just did a modification to make sure that this looks exactly the same as the band broadening in the first dimension. Instead of the modulation time, I have this A prime, and this A prime parameter is just all these terms that are here, and this is the modulation time. So when we plug in all the equations, we want to know how is this going to affect my total band broadening. So if you are in gradient for the first dimension or for the second dimension, the only thing they have to change is this A prime or A. So if you are in first dimension, this is A, and you are in the second dimension, this is A prime. You can get the peak capacity in gradient in the first or the second dimension. That's very simple. The only thing that happens is that the band broadening that you have is a little bit bigger because you have this undersampling in the first dimension, or because you have this injection band broadening in the second. I'm going to skip these maths. This is Thursday after party, so I'm just going to... So something similar happens if you have isocratic elution in the first or the second dimension, but I'm going to skip these maths. So let's go to the results. So what we did was a simulation in which we were using different modulation times, and we were saying, okay, let's see what exactly happens if you change the modulation time. So first thing, peaks get broader in the first dimension, peaks get broader in the second dimension, but of course something that you were saying about hard cutting or two-dimensional chromatography dilemma if you have more time in the second dimension because you have bigger, larger modulation times, of course having more time means that you have more peak capacity in the second dimension. So it's a little bit contradictory with these. So it's different effects that are affected by the modulation time. So if you plug in all the equations together, and we did a simulation in which we were studying different column dimensions in the first dimension, in the second dimension, also particle sizes in the first dimension, in the second dimension, column diameters in the first and the second dimension, and also different modulation times. This is what I explained with Heineken and Amstel beer, but now it's total peak capacity analysis time. Remember, we want to be here, having great peak capacities in a fast way. These are all the experiments, and this is what is called the breadfront. So this is what we get. So these are non-Pareto experiments. This is what is called forbidden zone. If you reflect about that, this is very similar to what Professor Smet has been explaining about kinetic plots. In my opinion, the kinetic plots is nothing else than a Pareto plot, which was invented long, long ago, because we have two objectives to optimize, and this is the limit of our possibilities. This is what is called forbidden zone, in the sense that the same example I was saying, with 50 euros you cannot get that amount of beer. Any shop that you go around Amsterdam, you're not going to get there. So this is the limit. So looking at these, so if you just inspect what is the values of the optimal diameters in the first dimension column and the second dimension column, and what are the optimal particle sizes in the first and the second dimension column, and what are the optimal modulation times, you see that immediately one effect appears, which is to make things optimal, at least from this perspective, the first dimension column the diameter should be very, very small, and the second dimension column the diameter should be very, very large. I'm going to explain. So in the end, this is not really optimal because it means that you have to have very high flow rates. I'm going to explain the solution for that. But in principle, looking only to your time and looking only to your peak capacity, the first dimension should be very, very thin in terms of diameter, and your second dimension should be broader. And also, that's known in chromatography, so if you want to have long analysis times, you need longer columns and you need bigger particle sizes. If you want to be fast, which is what happens in the second dimension, because you want to have fast analysis, you have to have smaller columns, so the length should be very, very small, and smaller particle sizes. Remember that I fixed the pressure of 400 bars, so it means that I use the 400 bars, making the particle sizes smaller and smaller, and making the columns smaller and smaller, okay, to keep up with the 400 bars. Otherwise, I cannot make a long column with very small particle sizes. But that's known that for large, for difficult separations in which I don't care about the time, which is more or less what happens in the first dimension, because you want to be slow in the first dimension. The optimal particle sizes are bigger than in the second dimension. So let's pay attention to what happens to the modulation time. This is the optimal values of modulation time from my calculations along the Pareto front. So these are the total analysis time in minutes. This is the modulation time. This is the effect. So if you have longer or more complex separation, in which you want more separation power, you have to wait more, but the modulation time is a little bit bigger. This may be not the right plot, so what we did was saying how many cuts per peak are optimal. And surprisingly, we arrived to a point in which you say normally 2. And that's why I wanted to mention the question from that lady saying, how many cuts per peak do you have? And I think you were pretty close to the optimal. So in literature, you see normally people recommend to have 4 cuts per peak, which from the perspective of detecting a peak is what is needed. So you have a Gaussian peak in the first dimension, you want to know this Gaussian peak. Normally it's 4 cuts per peak. But from the perspective of the total peak capacity that you can get, it's better to undersample the first dimension a little bit more, have more time in the second dimension, and gain peak capacity. But not too much. So below 2 is going to be not optimal anymore. So that's the compensation between the time that you get in the first dimension, extra time that you get in the second dimension because you have larger modulation times, and the worsening in the first and the second dimension due to undersampling in the first dimension and due to band broadening of the injection due to injection in the second dimension. So there's one thing that I skipped, and I want to get back to that, was the diameters, the optimal diameters in the first and the second dimension. I was saying hey, I mean, the first dimension is very small in diameter, and the second dimension is very, very big. In fact, the optimal is always selecting the maximum value that I put there and say, hey, wait a sec. This is going to have a consequence, which is, of course, if the diameters are that different, that makes the flows that different, and that makes these band broadening smaller. That's why my system has been selecting the biggest possible diameter in the second dimension and the smallest possible diameter in the first. Because in that way, the flow in the first dimension respecting to the flow in the second dimension, this division is close to zero. That makes this term close to zero. The injection band broadening is indeed negligible. But you immediately say, wait a sec, with these conditions, the sample is diluted. This is not optimal. This is optimal from the point of view of time and peak capacity, which was what I put in my system. But this is not optimal from the point of view of dilution. So in this way, we are diluting the sample 50 times, and then this can have very bad consequences if you want to detect your peaks, because that's not optimal. It's optimal from the time and peak capacity, is not optimal from the dilution. So what I did was saying, okay, let's add in my trade-off plots another objective. So the beauty of Pareto optimization is that you can optimize using as many objectives as you want. That means that instead of having a Pareto plot in which you have just 2 objectives, you have 3. So in this case, you want to make the minimum dilution possible in your system, the maximum separation power possible in your system, and the minimum analysis time. So I want to be here, here, and there. In that sort of corner. But now it's in 3 dimensions, because instead of having just 2 objectives, we have 3. So we are going to have a Pareto front, which is going to be a surface. And this is what pops up. Yeah. So it's a kind of shape like this. So it's very steep at the very beginning. So that means that it is not too much worsening the peak capacity and the time if you just want to dilute the samples a little bit less. So if you situate in that surface, so going to dilution 80, which is terrible, you don't want that. Going to dilution to 20 or even 10, you are not sacrificing too much of peak capacity analysis time. When you want to go to lower and lower dilution, then you have to compromise peak capacity and time. So this is exactly, and the condition there, I'm not going to describe the optimal conditions, but it happens that if you go down in this surface, normally happens that the diameters in the first and the second dimension become more and more closer, because you are increasing your injection band broadening and decreasing your dilution. So it's again a compromise, but now within the 3 objectives. I'm an academic, and I know that when we academic publish things, they sometimes lay on the library as a nice piece of work. People just looked at that. That's very nice. But I know that I also been in industry. In fact, I also work for industry, and I know that industry has no time to calculate these things. That's why I spend some time build up a graphical user interface in which the user can select the optimal values that they want to optimize. So, for example, in here, you say, I want to use different column particle sizes. I want to use different internal diameters. These are the objectives that you want to optimize. So you can optimize the total peak capacity to minimize that, or to maximize the total peak capacity, minimize the analysis time, minimize dilution, for example, so on and so forth. So you put here the equations, you put here your parameters, and you get the surface. This software is for free. You can download it. It comes with instructions, so please send me an email if you are interested, because I am interested in getting your feedback. In fact, with Agilent, we are trying to improve the software because we want to add some boundary conditions so that the flow doesn't get that high, but things are solved if you use some sort of extra objective like dilution. And there's one thing that happens that I just didn't mention, which is the effects of focusing. Remember, I was saying to make sure that the injection band broadening is small, we have to use very low flow rates in the first dimension, very high flow rates in the second dimension. That makes this term negligible. Another way to make this term negligible is to make sure that you have focusing. So if your first dimension eluent is a very weak eluent for the second dimension, you get the focusing effect. So there's a modification of this formula that takes into account the focusing. In fact, this slide is old. It's in the new software that I have. You can add here the focusing effect, which is a parameter here. It's all in the paper. I'm not going into the details. And that makes your life easier in terms of how much can I dilute my sample, or how different should the two diameters of the column should be. So I'm just going to conclude. In fact, it looks like I concluded before because of the slides were going up, but this is my conclusion. Now I'm serious. So the first thing is, that's a number that also Professor Tanaka arrived a couple of years ago when trying to optimize the system, knowing that the first dimension is undersampled due to the 2D effect. Also, we added the fact that the second dimension has a band broadening effect due to the 2D effect, and we arrived at the same number. In fact, I think Davis was publishing something using statistical overlap theory and arrived at around the same number. So it seems that the 2 cuts per peak, or the 1.5, or sometimes 2.3 cuts per peak, is the optimal way to go, okay, at least from this perspective. The second is that, of course, if you want to be optimal in terms of peak capacity and time, your system is not going to select the best conditions in terms of dilution, but the way to go of that is just to select an extra objective in your Pareto system. That makes you to work at suboptimal conditions from the point of view of time of peak capacity, but get fantastic benefits in terms of dilution. So the focusing effect, it is fantastic to get farther away from this trade-off between peak capacity, time, and dilution. Okay, just want to finish again thanking all my group, especially my co-authors, Peter Schoenmakers and Sjoerd van der Waal, for this paper. This paper is published in Analytical Chemistry 2010. And also Agilent Technologies for their kind invitation and for the lean of an instrument that we have. We have a lecture today. One of our postdocs, Sandra Poos, is in University of Valencia, but is now in Amsterdam. And he has a further talk about these systems today, this morning. Thanks for your attention.